Welcome back everyone to the next session of Days Cohort by Fluxus. Uh, we are in the course of discussing the tree data structures, and we have discussed the different types of trees. Yesterday we discussed about the previous day we discussed about the avial trees and red black trees. Now we'll move on to the implementation and the different coding aspect of trees. So today we will be discussing a brief on the tree traversals, and then when go on to its uh, coding part. So now let us start then. So what is tree traversal? Okay, when I say tree traversal, what do I mean by traversal? If I say, if I tell you that I want to traverse this array, what did I mean? What did I meant? Suppose I had an array that looks something like this, and I wanted to traverse this particular array. So what does this mean? This means that I want to index the zeroth element and then move on by increasing the index position. Then I want to index the element at position 1, then I want to get the element positioned at 2, and so on and so forth until and unless I reach the end of the array. In our case till a to a is the third index of my array. This was termed as traversing the array. That means accessing each and every elements of that particular data structure is known as traversal of that particular algorithm. In case of arrays, we were using a for loop, okay, which indexed at 0, incremented by 1 to go on with the assessment of my uh, yeah, basically uh, elements. Okay, so now herein what we are in the linked list, also to access the elements, that means to traverse the elements, what we were doing, we were just using a for loop to traverse the linked list. That means access each and every element of our uh, given linked list. So here in tree traversal, by tree traversal what I mean is, I want to access each and every element of my tree data structure. But unlike the linear structures, that means unlike the arrays, okay, Abhishek is asking for a brief on avial trees once again. Okay, Abhishek. So after I am done with tree traversals, I'll just brief you again on avial trees. Okay. 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 So where were I? So I was at, okay, what does traversal means? So traversal means accessing each and every element of a particular data structure. Now, whatever data structure we have discussed till now were arrays, linked lists, okay, and both of them, stacks and queues, all of them are linear data structures. That means if it is a linear data structure, then a single iteration of a loop is enough to index each and every element of the data structure. But in case of trees, the structure is not linear. The structure is not linear. And from now, whenever we are considering trees, we will be considering a binary tree. Okay. So when we're dealing with trees and binary trees in general, or binary search trees are also binary trees only, avial trees are also a special case of binary tree only. Okay, so when we're dealing with binary trees, what is the case, or trees, what is the case, that it first thing that comes to our mind is it is not a linear data structure. That means we cannot directly use a for loop or a loop. We cannot directly use a single loop indexed at 0 or say something going on to some length to access each and every element out of it. Why? Because suppose I start my indexing from here, from this. So this node will get traversed. The next is here. So what will happen? This will be getting dropped. So I can either traverse only these direction, or or this direction, or something like this. That is considering only the linear nodes in the linear path. But I'll have to eliminate all other nodes that are not in the linear path. So this is not a favorable traversal algorithm, because we are leaving out some nodes while we are trying to traverse this, as we were doing in case of arrays and linked lists. So that will not work. So in case of trees, what we need to do is we first need to study the traversal algorithms. Okay, the traversal algorithm. There are three algorithms which are developed, I also say traversal techniques, which are basic techniques which have been developed to traverse the tree data structure in an efficient manner, so that we do not leave on any of the nodes. Now, what are these? First one is, okay, let me just clear out the canvas. Okay, let me just clear out the canvas, and now let me start afresh. So when I am dealing with tree traversal, so there are three base algorithms which we will be using, either of the two. Okay, so first of all, any graph, and tree is a special case of a graph only. So any graph, there are basically two types of traversals. Okay, the first one being a depth first search approach. Second one is the breadth first search approach. For now, you do not have to ponder upon what are these two. We will be discussing them in detail, okay, after we are finished with the current topic in hand. Okay, you just remember this key. All the three traversal techniques that we are currently dealing with belong to the depth first search approach. Okay, so now let's start with the three techniques. Okay, so there are three techniques basically. So the first one is known as an in order traversal. The first one is known as an in order traversal, which is just a kind of a depth first search approach. What is a depth first search approach? I'll discuss after I have finished discussing in order preorder and the other tools. Okay, now what is a in order traversal? Okay, what in order traversal tells us is key, what you do while traversing any given tree. What you do is, suppose this is your tree, this is your tree, suppose it is numbered something like this, A, B and C. What you do is you first traverse the left subtree, then the root, and then the right subtree. So what in order means is we follow this particular thing, LRR, which means left, then root, and then right. You can also name it as LRRT to remember that the last one is a right. Okay, now what does left root right means? That while traversing this particular tree, what we will be doing is we will doing like this: first the left node, which is B, then the root node, which is A, and then the right node, which is C. So this will be the in order traversal of this particular tree. Let's suppose I have a larger tree. I have a larger tree which looks something like this. uh, we have one of the elements here, 1, then I have 2, then I am having 3 here. Let's suppose this also has some children here, 4, then 5, then 6, then 7. So while traversing, what we have to keep in mind, that we will traverse in this fashion: left, root, and then right. So what will happen is, first, which is the base root, one is the base root. So first we will traverse the left subtree of this particular thing, then we will traverse the right subtree following the in order traversal principles. Next, what we will do is, when we will enter the left subtree, we find another subtree here with 2 at 2 as the root. So what we do is we perform an in order traversal for this particular subtree also, starting from here, this particular tree I'm dealing with. Okay, when I reach this subtree, I get another tree which is rooted at a root 2. So what I'll do is I'll first perform the in order traversal of this particular thing, then the root, then the right. So in right also I am having a subtree. So what I'll do is again perform the in-order traversal of the right subtree. So it will look something like this. For the left subtree, the in-order traversal is 4, 2, and 5. This is the whole left of the main tree. Now 1, the root of the main tree, and now on the right direction. In right, what is happening? Right, I want to get the in-order traversal of the right subtree. So what will be happening here? It will be 6, 3, and 7. Its left, its root, and its right. So what I'll do is I'll now replace this with 4, 2, 5, 1, 6, 3, and 7. So this will be the in-order traversal of this particular tree. Any problems in order traversal? If not, then we'll move on to the other two. And if in order is clear, then other two will be clear in just a seconds, because the technique remains the same. If you're comfortable with getting the in-order traversal of the second tree that I discussed here, this one, so you will also be comfortable in the other two. Any doubts still here? Okay, so let me then proceed. Okay, so the next one is something known as a pre-order tree traversal. A pre-order tree traversal. So okay, so I'll just be updating this particular structure only. So when we are dealing with a pre-order tree traversal, what I'm dealing with here is I'll follow this order. This order, what's the order? In pre-order, what I do, I place the root first and then the left and right roots. So what I do is I perform something like this: first the root, then the left one, okay, and then the right one. So for this, what is the pre-order traversal? It is first the root, which is A, then the left one, which is B, and then the right one, which is C. Now here, how we'll perform the pre-order traversal? First left, root, and sorry, my mistake. Root, left, and right. So first write down the root node, then the left and the right. Then for the perform the same thing for the left subtree, 4 to 5. So for this, the left one pre-order traversal will be 2, 4, and 5. For the right subtree, the traversal will be 3, 6, and 7. So for the same tree, you can see the difference in order and the pre-order traversals. So this is root, left, and right. Okay, any doubts still here? This is what I said. If in order is clear, then pre-order and the next one that we are going to discuss here, that is post order traversal, which will be nothing but left, which is nothing but left, right, and then root. So if in order is clear, then I don't think pre-order would be much of a hurdle. And now if pre-order is clear, I don't think post-order will be much of a hurdle. So let me just discuss post-order now. Just going to discuss the post-order now. So first let me complete with the theoretical parts, then I'll move on with questions, Abhishek. So now there is a post order traversal. And what is post order traversal? It is just first the left part, then the right part, and then the root. So for this particular tree, what will be the post order traversal? It will be first B, then right, that is C, and then root, then this is A. For this particular tree, or trees that are more branched out, it will be something like this. First the left, then the right, then the root. And the root here is 1. Then we perform post order for the left subtree, which comes out to be 4, then 5, then 2. 4, 5, 2. For the right one, it is 6, 3, and 7. The tree is 6, 3, and 7. So this is the tree. So the post order for this is 6, 7, and 3. So 6, 7, 3, and now it is 1. So this is the post order traversal for this particular tree. Why 4, 2, 5? 4, 2, 5, 1, 6, 7, 3. Abhishek, this answer is not correct because your second one, the second element that I have put here, 4 to 5, it is the in order traversal of the left subtree, not the post order traversal. Okay. So with this, we finish with uh, the 3 traversal techniques. Okay. Now, where are all of these used? So So in case of a binary search tree, when you do the in order traversal of a binary search tree, what will happen? All the left elements are lesser than the root and all the right elements are the greater than the root. So if we are doing left, root and right, what is happening is indirectly we are printing the elements of the tree in the ascending order. So this is what in order traversal, one of the use cases of in order traversal. Okay, whenever you are posed with a problem wherein we have to print the elements of the binary search tree in ascending order, what we will do is we will just perform in order traversal of it. Now, second, what's the use case of pre-order traversal? So, whenever you are assigned with a task to perform deep copy of an tree or copy this tree into another tree, so you do a pre-order traversal. Okay, and the use case of post order, the use case of post order is whenever you are trying to delete the tree, whenever you are trying to delete the tree, what we perform is we first delete the left part, then we delete the right part, then we delete the node. Because if I delete the node first, so what will happen? I'll lose the information about the children then. So while deleting the post order is generally used for deleting a tree. Okay, first we delete the left or the right part, so left, right, then we first delete them, then we delete the root and then proceed in the same fashion. Pre-order, this was used, I have already discussed what's the use of pre-order. The use of pre-order is whenever you are tasked with copy, deep copy, this type of questions. And in order traversal, it is used for printing the BST in ascending order. The ascending order BST, whenever we are tasked to perform something like this, we perform an in order traversal of a binary search tree. Okay. And what's the complexity of these problems? The complexity is just an O of n because we are just traversing uh, each and every node of a tree. Okay. Now, what is an important factor here is how do we how do we uh, perform the in order, post order, and pre order via coding. Okay. So let me just fire my terminal, fire my IDE, and then we'll move on to the coding part. In the meanwhile, if you all have any doubts, questions, or anything such like that, you all are free to ask them. Okay, no, this was not the case. On that only I am going to discuss, Abhishek, right now. Okay. So we are good to go now. I guess you all might be having some problems seeing the. Just tell me when it is clear. Is the text clear? Not you all are free to ask me to change them. Okay. So let us start. So I'll code them as separate functions. Okay. So let's first discuss what is in order traverse. How do we code the in order traverse? Okay. So what we need to do in an in order traversal while performing in order traversal of a tree. So we need to get the root node. Need to get the root node. Okay. And then what we do is let's suppose that we have constructed our tree as a structure. Okay, so what we will do is we'll receive the node type pointer, the structure type pointer to the root node or whichever node we want to perform our in order traversal. Okay, suppose we are receiving such a node which is null, which is null. Okay, so what will happen is if suppose we get such a node which is null, means that the node contains nothing. The node contains nothing. In such a case, what is happening? We have reached the end of the leaf node. So what we will do, we will just return from this particular node. We are not concerned with such a node. But if this is not the case, if this is not the case, means we are not at the end of the tree. We are not at any such node which is not present in the tree. Okay, so what we will do is we will just make, we'll just perform a in order traversal at this particular node. We'll treat this particular node as the new root of the subtree. Okay, what I am discussing here is okay that if I reach such a node that is not pointing to anything, that which is a null, that means we are not at a particular node. But suppose we are at a particular node which is not null. So what do we need to do? We need to perform an in order traversal in a subtree with this particular node as the root node. So what I'll do here is we'll perform a in order traversal with this particular node as the root node. So what we'll do is we'll again call the same function recursively. We'll again call this particular function recursively. Okay, with which node? With the left node. With the left node. And I think this indexing operator in case of pointers is clear to you all. Okay, so what we'll do, we will just supply the left. Then what we will do, will now, what is the in order traverse? It is left, root, right. So root is the particular particular node where we are already there. So what we'll do is we'll just print the root. So where is the root now? The root is at the node where we are currently there. So we'll just what we'll do is we'll just print the data at the node, whichever node we are trying to implement as the root of the subtree. And then we will again perform an in-order traversal where on the right subtree. Okay, so this will be node ka right. Okay, and hence 10. This is only we need to do. This is the only thing we need to do. This is the beauty of recursion. What I am doing is I am receiving one node. I'm just checking whether this node is a specific node or not, whether it is a node that contains a data or not. If it will contain a data, what we will do, we will just call the in-order traversal to the left subtree, to the right subtree, and thus print that particular data. And why is this an in-order traversal? Because we are performing the left first, then the root, and then the right one. So this is doing what? This is just doing the left. What this is doing? This is just doing the right, root. And what this particular line is doing? This particular line is doing a right. So left root right is what in-order traversal is all about. Now let me implement a post order and pre-order now. So let me just copy this particular function only. Okay, and we will just apply pre-order now. So what was a pre-order traversal? If you remember, pre-order traversal was nothing, just root left and right. Pre-order was a root left and right. So what we'll do in this case is, this particular case is, we'll just perform the root first, then the left right. So what I have to do is I just have to delete this particular thing from here. Okay, and perform this before performing the recursive in order traversal of the left subtree or the right subtree. So now I'm performing root left right, and hence I am performing the pre-order traversal of the tree. Now let me just implement the post-order traversal. This is the post-order traversal. And what is post-order traversal? If you all remember, post-order traversal was nothing, just a left, right, and root. This was all about the post-order traversal. So while doing post-order traversal, what I'll do is I'll just perform recursive traversals first for the left subtree, then for the right subtree, and then I'll do this for the root. I'll just, then after that I'll print the root. Okay, and I think I missed some more changes. The changes will be I have to change the name of functions here everywhere. So this will be pre-order, and this will be also a pre-order. Here both of them will be post order traversals. Any doubts still here in the implementation part? I guess not, because I have just codified whatever I have discussed theoretically above. Okay, so this is what is a recursive implementation of the traversal algorithms. Sometimes you may get asked that you need to perform traversals, but what we need to do instead is you need to perform traversals not using recursions, not using a recursion, but without using recursion. So how will you do this? So this is one of the typical cases. Suppose I ask you, I have discussed the in-order traversal, pre-order traversal, and post-order traversals. Now I ask you that you are tasked with a task that you need to perform the in-order traversal of a tree, but you cannot use recursion as an approach. You need to deal with an in-order traversal without using recursion. And herein gets into the concept of data structures. Okay, so let me just discuss this part now. That how will you, this is one of the important questions from problems point of view also. Okay, how to perform an in-order traversal of a tree, without using recursion, because recursion simplifies my tasks. Okay, and whatever simplifies my tasks is out of the core concept of companies that they will ask this particular simple thing. Okay, so uh, now if I am dealing with recursion, okay, so what is happening in the backend? In the backend, what happens is कि we all have studied recursion, and we have studied something on the recursion trees, recursion stacks. So how does recursion happen? Recursion takes use of the memory heap and calls stacks, keeps the operations in this stack until and unless it reaches a base case. So in our case, what's the base case here? The base case is this one. Until and unless we reach a node that is not holding any data, which is null in nature, will be uh, recursively storing all the nodes in the stack, recursive stack. So what we need to do is we just need, if I need to remove recursion from here, so what I'll do, one simple approach is I'll be using a stack from myself, from my side only. What I'll tell the program code that you do not need to perform recursion, you do not need to store the data in a recursive stack on your own implicitly, but I'll explicitly create a stack into which you need to insert your nodes, so that the main funda remains the same, how you are dealing with recursion, but the implementation looks, whatever implementation I'm doing here will contain not a single line that looks like a recursion implementation. So we'll do something like this. We will be using a stack from our end only for explicitly, and then we'll be performing the in-order traversal of the tree. Okay, now, so how to perform this thing? So algorithm is a simple thing. First of all, why I'm using a stack? Because I need to replace recursion. I do not have to use recursion. So what I'll do is I'll not use recursion. I'll just use iterations, but I'll explicitly call the recursive stack. So how to call the recursive stack? By creating a stack from my end only. So first step is to use a stack. Now whichever node we are currently at, that is fed to my system, I'll take it as root. Why? Because I am not dealing with what was the structure before, what will be the structure after. Whichever node I am receiving, I'll be dealing with only this structure. In recursion also I am doing this only. In recursive implementation also I was dealing with this only. I was receiving a node. If that node doesn't contain the data, so I was just considering that this is not a node, and I was exiting from the recursion. But if contained a data, what I did, I performed another recursive call to the left and another recursive call to the right. So I am only dealing with this particular structure here. I am only concerned with this structure. I am not dealing with any other structure now. So what I'll do is I'll consider whichever node I am getting, I'll consider that as the root node. Okay, whichever node I am currently at. Okay, now what I'll do, I'll perform the stack. Suppose the stack's name is S. So what I'll do is I'll just perform a push operation with the current node. Whichever node is my current node, that whichever node I am considering as the root of the tree, subtree. What I'll do is I'll push that node into the stack. Okay, and while pushing, what I'll do is I'll just update my current. I'll just update my current as currents left. Okay, and this node will also be initialized as current. Okay, initially this will be treated as current. Okay, so I'll push the current node. Let me just write it as current only here. So what I'm doing is whichever structure that I'm receiving here like this. So I'll consider the root node of this particular substructure as the current node. Then what I'll do, I'll push that current node into my stack, and then perform a simple iteration, that is current equals to current ka left. Okay, then I'll again check. Okay, that if that particular current, suppose after some time, what will happen is I'll reach a node whose left is nothing. It doesn't have a child. This was a leaf node. Then it will not have any left or right childs. So if I perform current ka left, so what will happen? Null will be assigned to current. So this is my fourth step. If at any given step current becomes null, that means the previous node was a leaf node. Okay, and at this particular stage, and at this particular stage I look at my stack, and if this stack is not empty, if this stack is not empty, that means I have elements in my stack. I have reached a leaf node and I have elements in this stack. So what I'll do is I'll just print the stacks popped out element. I'll just pop out the element from the stack and print it. Now what I'll do is I'll perform an operation, that is whatever element is popped out, set the new current as popped element ka right. And now again what I have to do is I have to again perform this particular thing here. I'll again loop till here. Again, whichever node I am here, I'll push that node into the stack, perform a left, iterate the left, update the current as the current elements left. Then I'll just do the same thing until and unless I reach a node which is equals to null. And at that particular step, if my stack is not empty, what I'll do, I'll just pop out one of the elements from the stack, and then again update my current as the right element of that particular element, right pointer of that particular element, and we'll go on until and unless my current is null. That means I have reached a leaf node, and this thing is not present. That means my stack becomes empty. So in simpler terms, what I am doing is, I think this might get confused for you all. Let me just check with an example. Suppose this is my tree. Okay. So what I need to do here is, first of all, what will be passed? One will be passed. So what I'll do is I'll push one to my stack. And there is a current. What I'll update current with, I'll update, and there is a root. There is a current. So what's my root here? Root is 1. I inserted my root into the stack. Now I'll update my current as 1 ka next. So 1 ka left. So what's 1 ka left? 1 ka left is 2. Okay. Now I'll check whether 2 is null. So no, this is false. So if this is false, what I'll do is I'll again consider this 2 as my root element. I'll insert 2 inside the stack, and I update my current as the current elements left. So what's current elements left? It's 4. Now what we'll do is, again, we'll check whether 4 equals to null. No, 4 is not null. So what we need to do is, we'll need to update my root as 4. And now I'll insert it is 4 ka left. Now 4 ka left is null, because there are no children of 4. So now we'll check, is null equal to null? Is my current equal to null? Yes, the current is equal to null. So in this case, what I'll need to do, perform 2 operations. First, I need to check whether my stack is empty or not. So I'll just check. My current becomes empty here. Null here. So I'll check, is my stack empty? No, the stack is not empty. So what I'll do is I'll just pop one of the elements from the stack. So I pop out 4. Popping means printing out 4. I'll print out 4, and now what I'll do is, suppose 4 is printed out. This is my console. Now what I'll do is I'll update my current as 4 ka right. 4 ka right. Again, is 4 ka right an element? No, it is a root. It is a null. So again, this thing will only happen. The current is null here. So what we will do is, we will pop out the element from the stack. So what will be popped out? 2 will be popped out, and 2 will be printed. So 4 and 2 are not present in this stack now. So now what we need to perform? Now new current is 2 ka right. So what's 2 ka right now? 2 ka right is 5. So it will be check, is 5 equal to null? No, 5 is not equal to null. So what will happen? 5 will get pushed into the stack. Now what will happen? I'll update my current as current equals to current ka left. Again, this particular thing will happen. Now null, again null. So what will happen? 5 will get popped out. 5 gets popped out. Now again we reach to 1. 1 gets popped out. And now if one gets popped out, now what we will do, we will just perform one car right, and one car right is 3, and 3 is not null. So if it is not null, what will happen, 3 will get pushed into the stack. Now 3 next current will be set to 3 car left. The 3 car left is 6, this is also not null, so 6 will be getting pushed into the stack. Now 6 car left, 6 car left is a null, 6 car left is a null. And is the stack empty? No, the stack is not empty. So what will happen, just pop out the element from the stack. So 6 will be popped out, 6 will be popped out. Now what we perform, we perform 6 equals current equals to 6 ka right. Now 6 ka right is also a null, 6 ka right is also a null, and the stack is not empty. So what I do, I perform a pop operation on this stack. So this stack becomes now empty. If I perform a pop operation, now what I do, I go back, I go back to 3 ka right now. So now 3 ka right is 7. Is 7 null? 7 is not null. So what will happen, 7 will be get pushed to the stack. Now if 7 gets pushed to the stack, now what I have to do, I have to perform 7 ka left. Current is 7 ka left. Now 7 ka left is a null, 7 ka left is a null, and stack is not empty. So what we need to do, we need to perform a pop operation here. So we perform a pop operation here. Now what we need to do, we need to perform 7 ka right. Now 7 ka right is also null, 7 ka right is also null, and the stack is empty. If the stack is empty and null, so this ends my process here. So what we perform, we reach the fifth step. That is, if my current becomes a null and my stack is also empty, then we end the operation. Otherwise, we go on doing this thing, pushing the element into the stack, updating the current as the left of that particular element, then again checking whether my left is null or not. If it is null, then we check whether my stack is empty or not, and we do this again and again, until and unless we reach a state whether my current is also null and the stack is also empty. Okay. So any doubts still here? If not, then we will proceed on to the uh, coding part. So if you are not asking any doubts, we'll move on to the coding part. uh, Okay, Abhishek is asking, so we need to define left and right data part in the program first. Yes, Abhishek, we need to define the structure of my tree. But as I have already discussed that in the previous lectures, I didn't need to do that. I just perform the left pre-order, post-order, in order traversal of the tree, so that we can move on to some major questions out there. Okay, so I'll just increase go to the algorithm part here. Okay, So what was our task? Our task is to first initialize the stack and then move on with my uh, the current, checking the stack whether it is empty or not, performing some operations if the stack is empty, performing some operations if the stack is not empty, okay, and performing some operations if my current is not enough. So we'll just code that part now. Okay, so let's start. Okay, so let's start. Okay, let me move at the top only. Okay, so there I am coding a void only. This will be void in order without recursion. This is the my function here. Okay, so there also what I'll receive, I'll just receive a node. Here also I'll receive a node. So let me receive a node here. So I'm receiving a node. Okay. I received a node here. Okay, now I received a node here. Now what will happen? First, I have to initialize a stack. So let me make use of the stack STL that we have studied already. So I'll declare a stack of node pointer types data, and let that be called S. Now what I'll do is I have to set the root element of the the root element. Okay, the root whichever I have received, the node that I have received now, I have to set that as my current element, current node. So what I'll do is I'll first declare one current node first. So let me declare a current, and this current is nothing but I have to make this equal to my node, whichever node I have received. Okay, now I have to perform some operations. What are the operations? First one will be if my current is not equal to null. Okay, my current is not null, so what I have to do is I have to push the elements of the stack, push the current element into the stack, and update the current as current ka left. Okay, so I'll do this thing only. So I have to perform these operations until and unless which, until and unless my current is not equal to null. If my current equals to null, then I have to do something else. I have to check whether my stack is empty or not. Okay, so let me just check that also here only. Okay, so when till when my current is not equal to null and till my stack is not empty, till my stack is not empty. Okay, so what I'll do here is I'll again perform the same operation while my current not equal to null. Then what you do is the what you just do, okay, you push the current element into the stack. You push the current element into the stack. Okay, and update your current as currents left. Update your current as currents left. Okay, this is only what we discussed. Okay, so if my current is not null, what I'll do, I'll just push that element into my stack and update my current as currents next. Next thing what I need to do is I need to, if my current is not null, if my current is not null, then this will happen. But if my current is null, what will happen? This particular thing will not get executed. And if my current is not null, what were I doing? I need to perform a, let me just look at the algorithm now, what I have written. So if my current is not null, what I need to do is, if my current is null, then what I need to do is I need to check whether my stack is empty. And if the stack is empty equals to false, then what I need to do is I need to perform a pop operation and perform the same thing with the right, update the current to its right. Okay, so here what I'll do is this checks for if my stack is empty equal to false. So if I am inside this while loop, this means that stack is not empty. Stack is not empty. Okay, I think I have not called the function correctly here. Okay, the stack is not empty. That means I need to only check whether my current is null or not. And if I have exited this loop, this means my current is null after I have reached this particular point. So here what I'll do is I'll just take out the current as the top element from my stack. Why top? Because top is the element which will be getting popped out. Now I'll do, I'll just pop out the element from my stack. Now what I need to do is I need to just print out, because this is my traversal. What I'll print out the currents. I'll just print out current ka data here. Okay, whichever data I am stored here. And now next what I need to do, I just need to update my current. I need to update my current as current ka right. As current ka right. This is only what we discussed. Okay, if my current is null and the stack is not empty, so what you do, you just pop out the element and perform a write operation. Make new current as the popped elements right. So this is only I'm doing here. What I'm doing is I'm storing the popped element that is popped out. I'm storing that in the current variable, and then I'm popping out. Then I'm printing out current, and then I'm changing the value of current to current. The currents right. I think current is confusing you all. Okay, now next what we need to do here is, if my current is null and my stack is empty, what I need to do, I need to end my operations. I need to end my function. So here what will happen, if my current becomes null, so this part will return in a false. And now if my current becomes stack is not empty, stack empty becomes true, then this part will return in a 1. And both, if both return in a 1, both return in 1. So what will happen, if current is null, this is a 0. If stack is not empty equal to 2, then this is 0. So what will happen, this while loop will never get executed, and if this while loop never gets executed, that means my program ends. So this is how we implement in order traversal without using recursion. Without using recursion, why? Because I'm just using whatever recursion is doing as the in the back end, and the hood I'm performing that using my explicitly defining an array, explicitly defining an stack. Similarly, you can perform post order and pre-order traversals. You just need to print your data at the right places. Okay, any doubts still here? If not, then we'll move on to the next question. So the next question will be, okay, let's do this question. This is an important question. So I'm not getting any doubts in the comment box. So I'll move on with the next question. So the next question is uh, to find the maximum depth of a tree. To find the maximum depth of a tree or height of a tree. Okay, the question is to find the max height of a tree. Now, what is a max height of a tree and what is a height of a tree basically? We have already discussed this thing. If anybody remembers it, what is the height of a tree? Height of the tree was starting from the root node. Starting from the root node, what is the longest distance? What is the longest distance that reaches one of the leaf nodes? This was the height of a tree. Now what we need to find out, what is the maximum height of the tree? The maximum height and height of the tree is are just the same thing. Now what was the maximum path? This is one of the concerns. If I remember, what was while counting the path? Were we counting the nodes or the number of edges? Does anybody remember this? While counting the length of a path, were we counting the number of nodes in that particular path or the number of edges in that particular path? So path, when we're dealing with a path, we are just interested in the number of edges. Okay, we are just interested in the edges. Okay, so what we need to do in our particular question here is nobody is replying in the comment box. Why? I think today's session is not interesting or what? If it is so, then please reply. I'll change the way of teaching then to make it a more interesting way. Okay, so nobody is replying, so I move on with the discussion only. So what we need to do here is we need to find the maximum height of a tree or find the height of the tree. So what algorithm I will be using here is I'll just be calling, I'll using a recursive implementation. What I'll do is find the height of my left tree, find the height of my left tree, then recursion of my height of a tree. This is my height of a tree. Okay, so what I'll do is in here, just find the height of my left tree, height of my right tree, and whichever is max, find the maximum of both, left and right, whichever is the highest, return me tag. And I'll do this recursively until unless I reach if my height is 0. The base case will be if my height is 0, so the max will also be 0 only. Okay, so this is only what we need to do. We just need to implement a recursive, we need to perform this thing recursively until and unless if the tree is empty, we will return 0. Otherwise what we will do is we will find the depth height of the left tree, then we will find the height of the right tree recursively, find the max of both of them, and at the last what I'll do, I'll just add 1 to the max depth, because for the current node I am performing the for the left tree and the right tree, no. So this whatever be the highest height till here, 1 will be added for my root node also. So this will be 1 plus max will be my uh, return value. This will be my maximum height or the maximum depth of my particular tree. So now let me implement this particular function also. Okay, so let us implement this particular function then. So let me just write this as max height tree, max height of a tree. So what I'll receive here is I'll again receive one node here. I'll receive one node. Okay, now what I need to do here is I need to implement this particular function. Hi guys, sorry if there were some internet issues from my side. I got disconnected. So as I was discussing the maximum height of a tree. This algorithm I was discussing. So I guess till where it was live. So I'll just repeat it once again. So what I'm doing here is I'm just constructing one function with name maximum height tree. I'm receiving a node in here as the parameter. Now I'm checking if that particular node is a null, is null. That means it doesn't contain any data. What I'm doing is I'm returning with a zero value. But if that is not a null, so what I'm doing is I'm recursively calling the height function. That is, I'm calculating the height for the left subtree, and I'm again calculating the height for the right subtree. Then I'm storing both of them in two different integer type data integer type variables. Now I'm calling the max function to calculate the maximum of both of these, whichever numbers they return, whichever is the left height, whatever is the left height and whatever is the right height. What I want to get here is which one is greater than which the other one. Okay, so this will return the maximum of both, return an integer that is the maximum of both. So what I'm doing is I'm just adding one to it. I'm adding one to it and then returning that particular thing. So whatever will be the maximum height of the left tree or the right tree, what I'm doing is I'm just adding one to it and returning this. Okay, so this is what how to calculate the maximum height of a particular tree. Okay, I guess this is particular algorithm is clear. So I think with this, one of the things might be clear with you all, that whenever we are dealing with trees, whenever we are dealing with trees, so at the start only, when I think in the first lecture only, I have told you that tree is a recursive data structure. Tree is a recursive data structure. And what does that mean? When I tell that tree is a recursive data structure, that means that if you are tasked with any problem, just think of a recursive solution to it. If I tell you how to find the length of the tree or the height of the tree, you if you go on, I'll use a counter c plus plus, do something like this, counter plus plus, it will be a long task. But you think with an recursive implementation in your mind, what will happen? Okay, I have a tree. The left and right trees are also subtrees are also a tree in themselves. So the height of this tree will be just one less than the height of the left tree or the right tree. What I'm doing is I'm just creating a recursive function here. In the similar fashion, whichever question you need to solve, you need to solve key, is that particular question solvable for the subtrees also? If it is solvable for the subtrees also, then you just think of a base case. In most of the cases, the base case will be this only if the node is null. Okay, and you just implement that thing. You just implement that thing using recursion, and your problem will be solved. So there is no little bit to no mathematics involved here, or any aptitude required here. You just need to think in a recursive manner, a recursive solution to every problem, and your maximum problems of a trees will be solved. Okay, if nothing can be implemented, you just if just a recursive definition cannot solve your problem, then think of it ki, do I need to implement some other algorithm here, whichever I have learned previous, that is like binary search or any other algorithm that you have already studied, if you need to implement that thing or not. Okay, but the core solution, the core structure of the solution will be a recursive solution in this manner only. Something will be called for the left part, something will be called for the right part. You will do some operations on it, and the majority of the cases, the base case will be this only. If the data at that particular, if that particular node is a null node. Okay, and most of your questions that are related to binaries trees will be solved. Okay, now Now, in the similar fashion only, let me ask you one question. Okay, suppose I want to tell you, okay, you are given with a tree, Okay, I'll supply with you the root node, and then I'll also give you an integer, say 3. And what you need to do is you need to print every node which is at a distance 3 from the node. You need to print only those nodes which are uh, only those nodes or all the nodes, which whatever be the question. You need to print all the nodes from the root node till that particular kth node. So if you go on thinking what will be the what will be the algorithm, it will be a very large longer task. But what I say you, what I am telling you, you just need to think in a recursive manner. So what I'll receive is, I'll not just receive the uh, let me just copy this thing, and so just keep this question in mind. I'm not dealing with any pen paper here. Okay, I will directly be coding the solution. Okay, in this particular thing only. So what I'm doing, what I'm telling is, I need to print all the nodes in a tree that are at k distance from the root node. So k nodes tree. Let me just name the function like this. So what I'll be receiving, I'll be receiving the root of the tree. I'll be receiving the root of the tree. Let me just okay, let me just keep it as a node only, and I'll also be receiving one integer, say k, that will represent the number of the distance till which I need to print the nodes. Okay, so how will my implementation change, the basic implementation change? Okay, the basic implementation will change in this fashion. Okay, what I am telling you, this will be the basic structure of my solution. So let me just write it in this fashion only. One for the right, one for the left. Now I'll be checking whether my root is null or not, because this will be my base case. But one more case will arise here. If either my root is null, or the distance that you have told me to print the nodes, the k, if that k is less than 0, means you've given me a negative distance. The negative distance is never possible. A negative distance is never possible in a tree. So in both the cases, what I'll do is, if my node is a null node, or the distance that you have told me to print the nodes is less than 0. So what I'll do is a negative number. So what I'll do is, I'll return 0. This is how I will update my base case. Now the next thing is, the root is not null. The root is containing some data. But what if the distance that you have told me to print is 0 only? So if it is 0, to what is that? What is the which node is at 0 distance from the root node? The root node itself. With the place at which I am sitting right now, this place is only at 0 distance from my place. So this is also one of the corner cases that I need to deal here. That if the user gives me a tree, the tree has data, the root node has data, but what if the thing that I need to print is sorry, I cannot write here written 0, because I am using a void, as I think I have used that thing only in previous things also. Sorry. I cannot use 0 here, because I have used the return type as void. So let me just check. So here no problem is there. Here also I have used just return, then okay. This is also okay. So I have just made mistakes in these two particular codes only. So if the distance that I need to print is 0, so what I need to do here is, first of the things that I need to do here is, I need to print the data that is stored at my particular node, because the node that is at distance 0 from the current node is nothing but the current node itself. And the next thing that I need to do is, I need to stop the iteration of the particular functions. I just need to return from this function. Now what if the node is not null, the node is the distance is not negative or 0? So in this case, what I'll do is, I'll just call this recursive function for the left subtree and for the right subtree, just by decreasing the value of k. Why? Because at the kth distance is my node. So whichever distance my left and right subtree will supply me will be one less than my kth distance. Okay, if I need to find the k nodes from my root node, okay, so one of that k nodes is my root node itself. So whichever number of nodes that I'll get from my left subtree will be just one less than my k nodes, and from the right subtree will also be one less than the k nodes. So here what I'll do, I'll call it for the left part, call it for the right part with just one element, one value less than the k that I have originally received, and I'll call this recursively. I do not need, as the value is void here, so I just need to, I guess I made a mistake here. It will be 0, but this will not be void. Only mistake here was this will not be void. Okay, because I need to get the left and right heights also, no. So that's why this will not be void. The return will be end. Otherwise, all the things were okay. Now, in this particular question, I'm not receiving anything out. So this is only what I need to do. So now I think this will be clear what I told you previously, that whenever we are dealing with any question of the trees, so we need to keep this particular structure in my mind. This will be the base case, null, then we have to return 0, and I need to recursively call the same function for the left and the right parts. Only thing will be we need to implement some corner cases, like in here for k equals to 0, and check some conditions. The base structure of every solution that we need to implement in trees will be this only. You just need to think of things that you need to add or subtract from the basic solution. Otherwise, as you can see, this is one of the templates of the solution. Just think it like this. Any given question in trees has this particular template only. And by the way, this is one of the important questions to print the k nodes at k distance from the root. I guess this was asked in various companies too. I'm not getting the company. I have got the company tag. So company tags are Amazon, Microsoft, Ola, Caps. See, this is one of the important problems. And what was the important problem? Important problem, nothing. Just I have to use the basic structure, basic recursive definition of the tree, and update, change two things. I'll receive 1k and call the recursive definitions will 1 less than the k. Nothing else. And this constitutes of one of the important questions. So you can think of it. Okay, how easy the questions of tree are if you understand the basic concepts and the basic theory there. Okay. Any doubts still here? If there are any doubts, kindly ask them in the comment section. Otherwise, we are good to end this session here. So one key point that I want you all to take from this session is what you can say take out from this session is the questions of trees are not hard in themselves. The only thing is you need to deal with what kind of traversal you need to perform there. Okay, and just think of trees as a recursive data structure, and remember the base structure of the solution, the solution template. I'm calling this as a solution template. There is a solution template for the solutions of the tree. You just need to append something in the base case. You just need to make some changes in the parameter list, and your questions will be solved. If the question is of basic trees, otherwise you just need to make some changes or use some concepts like binary search or any other thing that you have studied previously to solve the question, but the basic structure will be the same thing. You will have to solve for that particular node and then call that particular function recursively for the left subtree and for the right subtree. This is the basic structure. You first need to solve the question for that particular node and then call the same function recursively for the left part and for the right part. This is the basic structure by which we formulate our solutions of tree data structures. In case of any doubts, any misunderstandings, any confusion, kindly post them in the comment section. Otherwise, we are good to go. And tomorrow we will be discussing heaps. So tomorrow is also an important thing. Heap is just, you can think of heaps like a special case of trees only. Okay. So tomorrow we will be discussing heap and heap sort. You might have remembered that I have left some of the sorting algorithms while we were discussing sorting. Okay, as I have told you, because they require some additional knowledge of further data structures, and one of them is heap sort, which requires the knowledge of heap, and heap required the knowledge of trees. So now we are good with this particular understanding. We are good to go with to learn heaps and then heap sorting as a broader picture. So I am not getting any doubts in the comment sections. I may assume that you all do not have any doubts. So we end the session here. Good day, great day ahead. Good night. Great learning sessions. Thank you for attending. You will be receiving the attendance links in a short while. Okay, so don't. Thank you, Ravi. Thank you, Antara.